So again, this was the graphical representation of information retrieval that we started our discussion on this course with. So here, so far, we have discussed this document representation part. This part we have discussed. So basically, how a given set of document can be indexed after pre-processing the document is actually discussed already. This document representation is basically that involves the term selection, the linguistic preprocessing steps like applying stemming or applying stop word removal or not, and whether to keep the capitalized sentence, capitalized words as it is or not. This kind of decision makings were performed during this step, document representation. Basically, in short, we can say document representation, this part is involved making the decision of which terms to select to represent a document. And after that, we have made the index, basically an inverted index. We have written one code using a simple knowledge of using a simple hash table with Python. Together with that, we have discussed we have actually written the code using Lucene, how to make the index efficiently. In today's discussion, we'll be concentrating on this. So basically, today's discussion involves we'll be basically discussing this part. So how an information need can be transformed into a query. Although this part, like from the information need, such as how to find the square root of a number, maybe if this is the information need, how to represent the query, this will essentially we will be following a keyword based approach. Basically, we will be selecting some keywords from the information need to represent the query. But as we have seen, if the query queue is represented with multiple query terms, let's say Q1, Q2, up to say some n number of terms, then how to actually apply certain clause. For example, for the Boolean retrieval, we have seen and or clause, how to apply them efficiently, or how to actually apply them to have a better retrieval. This will be the discussion of today's topic. All right. So the query language, this one, is basically defines how user can describe their information need to the system. Note that this is the system. Essentially, this is the system. A retrieval system is essentially consisting of not actually this, only this is the retrieval system, the retrieval model. Although this indexing is performed by the retrieval system as well. I mean, this is also performed by the retrieval system. And this query transformation can also be taken care of by the retrieval system as a whole, such that this represented query, which I am referring to as the query language, can be used together with this retrieval model and the index of the collection to select certain documents which satisfies the information need of the user. So this query language can involve a Boolean clause if it is a Boolean query. It can involve simple query terms only. The document representation, this part is basically determines what is this indexing, this index is consisting of, that is how individual documents are represented in this index. There, the information regarding term occurrences and term frequencies can also be stored. I must say they will be stored for the rank retrieval. That will be the major focus of this course. Another thing that we will be seeing in today's class is the position or the term occurrence position of the term and how it is actually necessary. This we will be discussing in today's lecture. The index is basically the data structure, you can say, the essential operation that will be operated on that index will be the search, and an index should facilitate a quick finding of the document matching some queries. Note that this query is basically the query language that we have transformed the information need into. And retrieval model is basically the module in the information retrieval system that decides whether a document, based on its occurrence in this index, whether it is relevant to the query language or not. And if it is relevant, what is the degree of relevance? Is it highly relevant? Is it very lamely relevant? If it is just borderline document, if it is irrelevant, those decisions will be made by this retrieval model. So today's discussion, we will be concentrating on this process. So we started our discussion with this incidence matrix, term incidence matrix, where each row were containing the document IDs, and each column was basically each of the terms in the vocabulary. So we have seen that this is basically a term document, a term term incidence vector, and these are basically the document incidence vector using which we can perform retrievals. Making an inverted index like this, we have used the bag of words representation, which is we will be considering all the words and their occurrence in the corresponding document as the input to make this matrix, the term incidence or term document incidence matrix. Here, in the beginning, the discussion we started with, we were not storing the term frequency as such, as well as there is no location of the term where it is actually occurring was saved. What we were storing was essentially whether this term is occurring in this document or not. In general, if we say V as the vector, if we specify this term incidence matrix as V, Vij will be 1 if the term, if Tj is in Di, and otherwise it was 0. So this was the term incidence, term document incidence vector that we started with. And to make the corresponding query representation, we have used the boolean clause like and, or, and not, etc. So how the query processing was happening? So if it is a query, two-term queries such as say Q1 and Q2, we looked at its term incidence vector, its term incidence vector like this, and we have performed a boolean clause, let's say XX. Based on the need, we have applied either and or, right? This was also, I mean, this can also be said as a bitmap index. Later on, we extended that bitmap index or the term document incidence matrix with storing the document frequency. So what was the motivation of storing the document frequency? Essentially, earlier each document was represented in each row. Now we have actually I mean, we get rid of this individual row information. Instead, what we stored is basically a posting list. These are basically the posting list or postings. So in the postings, for each of the term, we stored the document ID in which it is occurring, and using the document frequency of that term, we can actually make an efficient merging, and we can save some space as well that we have discussed earlier. Now, to extend that further, we discussed on storing the term frequency as well. For such in this example, the term say abacus. What we can see is the term abacus is present only once in a document. The document ID is 254, and in this 254 document, it is again occurring only once. So here we have said, I mean, we have discussed this earlier, the collection frequency of the term, let's basically say it generally as X. Collection frequency is 1, that is basically the total number of times the word is occurring in the whole collection. The document frequency of X is also 1, that is, it is only occurring in one document, and the term frequency of the term in this document having doc ID 254 is also 1. Take another example for this, say ABBA. Here the document frequency is 3. That means the term ABBA or ABBA, whatever you want to say it like, is basically occurring in 3 documents. Document 1, document 2, document 3. These are the doc IDs, and the second column is basically the corresponding term frequency of the term ABBA or ABBA in the corresponding document. That is, ABBA is present 5 times in the document having doc ID 43, 6 times in the document having document ID 576, and so on. So the collection frequency of the term, again X, in this case is basically 5 plus 6 plus 3, so which is basically 14. The document frequency is already 3, we have seen, and these are basically the term frequencies. The term frequency basically TF of X in the first document, so 43 is 5, and so on for the other 2 documents. Now, how this is an advanced version of this? Earlier, it was only storing whether the term is present in the document or not. It was not storing whether the term is occurring in the document, whether it is once or twice or 100 times. How many times the term is occurring in the document was not stored in this simple bitmap index. But here we are storing that. And we have already very briefly discussed that if let's say Q is a query term, let's say Q is a query term, and it has been seen that if the term frequency of Q in a document, say D1, is greater than the term frequency of the same term Q in another document, say D2, then generally it has been seen that the relevance of D1 for Q, or for at least, yeah, we can say capital Q here, will be greater than the relevance of D2. In simple English, I can say that if a query term Q is occurring in a document more number of times, then it is most likely to be more relevant than the other document. Okay. So based on this information, based on this TF that we are storing here, we can actually have a ranked retrieval. But again, we are considering a boolean retrieval, that is whether it is present or not. And the presence is basically considered as based on or a factor of this term frequency. So boolean can be a misleading word here, but by boolean I am specifying whether it is absent or present. In case of presence, we are also considering its term frequency to make it a ranked retrieval. Earlier it was not possible for this bitmap index, but for this index where we are storing this extra information, where we will be able to actually achieve this ranked retrieval in this scenario. Now, what about other type of queries or query operators? So, as you might understand that only using this and or and not is too restrictive. Too restrictive in the sense, if we allow too much flexibility or independence, we might be actually hurting the precision. And if we make it more restricted, that is less number of documents will be retrieved, then we will be hurting the recall. Now, what is precision and what is recall will be discussed elaboratively in the second part of the course during the evaluation part. But just to give you a very brief about these two keywords, which is very important in information retrieval or any other machine learning tasks as well. Precision is the metric which specifies how precise your result is. In other words, formally, let's say you have retrieved, say, n number of documents, and among them, say, r number of documents are relevant. R is the total number of relevant document retrieved, relevant doc retrieved, and n is, say, total number of retrieved. Then precision is basically R by n. Basically, out of the document you have retrieved, how many of them are relevant? And for recall, pardon my bad naming here, I should be relevant document retrieved. I can actually have some other notation here as well, but for the time being, just to specify, recall is, let's say, in the collection there are, say, total m number of relevant document. Total m rel docs present in the system, in the corpus. Then recall is out of M, how many of relevant document you have basically retrieved. So just make it rel, and this is basically precision, this is basically recall. So this will be discussed later on with more more focus. The thing that I want to highlight here is basically if we specify this and or, and means if I specify a query like x and y, it is too restrictive. Why? Because a document should contain both the query terms. But we have already discussed, we already know from our intuition that all the query terms are not that much useful. Right. So if we are providing a query like, say, let's say the movie Dark Knight review. So the query is containing 5 terms. Although this term is basically a stop word, we can actually ignore that. But the more important terms are Dark Knight and also review. This term movie is not actually that much important. But if we use an AND operator, we will be ignoring those documents which are containing these 3 terms, which are the most important terms in this query. That's why AND is very much restrictive. Also, if we specify OR, so just to give you, just to again recap, if we specify AND, we might be hurting the recall. Why? Because less number of documents will be, more number of documents will be filtered because of absence of either of the query terms. And if we specify OR for the same query, and let's consider again the is ignored, then again all the documents containing the term movie, dark, night, review, all these 4 query terms are also will also be evaluated or also be selected. That's why it will be actually good for the recall, but it will be hurting the precision. Why? Because here total number of retrieved in case we use OR will be a very large value, and in the denominator, as n is in the denominator, it will be actually hurting the precision altogether. This will be, as I said, will be discussed later on as well. So essentially, to overcome this problem, there are other types of query operators as well, like proximity operator, field restriction, and wildcard operator. So for the proximity operator, we can actually specify basically the way the query terms we want to be present in the document. Let's say the given query is, say, information science, and we want them to be at most far from each other by, say, n number of words in between. Let me rephrase that once again. In general, if we want a query with the words A and B such that A must appear no more than n terms before B, then we can actually use this ordered window proximity operator. OW is basically the short form of ordered window. OW/n is basically specifying that for this A, OW/n B is basically specifying A, the query term A must appear no more than n terms before B. For example, here information OW2 signs, that means these two should be appearing, like information will be appearing before signs, and in between these two terms there must be at most two terms. For example, this is a occurrence which will be basically considered by this query. Information library signs, where there is only one word in between. This will also be selected. Information signs, where there is no words in between them. Here, this is actually problematic. So here are two extra terms in between. So pardon for my misspelling, miswording. This is basically specifying whether n number of times. So here n specifies the space in between. So here two times, two words are appearing. If we specify this ordered window in a way that it's no more than n times, then it will be also selected. But together with that, let me tell you this: for some retrieval systems or in some terminology, we might refer to this as a non-occurrence or non-overlap, because here n is considered as an upper bound, which is basically basically a closed upper bound. But here, for the ordered window, this will never be selected, because information is occurring before after signs, but it is ordered window. Another type of proximity query is basically, or proximity operator is basically phrase operator, where we will be just specifying this AB. For example, in Google, if you want to search with a query, say X and Y, and you want them to occur together, one way of ensuring that is put a double quote and then specify XY. This actually is a phrase operator which is specifying that only those documents will be considered where these two terms are occurring together as a phrase. For example, if you want to search for the term Hong Kong, if you search simply in the general scenario, this Hong Kong can also consider the document having the term not the Hong but King. But if you want to specify that you want them to be considered as a phrase, you should be specifying this in a double quote. So here, as a result, information signs, only this will be considered. None of the other three will be considered if we specify a phrase operator. Also, this is actually equivalent to ordered window 1. So again, this is true for this scenario where we are not selecting this. Now, ordered window 1 means there won't be any words in between, right? And ordered window 2 means, as we have seen, there will be at most one term occurring in between. That's why this was a match and this was not a match based on that. For the phrase query, it is also basically a similar to ordered window operator with the value of n set to, or the value of the window set to 1. Another obvious variant is unordered window. It is same as the ordered window, but the presence of the terms can be actually, it's not actually important. Whether the first term will be appearing in the first, that is not actually necessary. So as an example, information unordered window 2 signs will actually match this. Information and library signs, this will not be matched, because I'm considering that two thing like here, this one. But if we are considering that including the window, that this can also match, and this will also match, which was earlier skipped here because it is unordered. So considering this posting list that we have made in our inverted index, this cannot actually handle proximity operators. So what additional information do we need? Anyone? So here in this inverted index, in the inverted index that we have made, we were storing the term, the document frequency, the document ID in the postings together with its term frequency. Now this cannot actually handle this kind of a proximity operator. So if I want to check for this unordered window or the phrase window or the phrase operator, this will not be sufficient. So what additional information do we need? Anyone?
Index of each term in the document.
Sorry, can you please repeat once again?
Index of each term in the document.
Index of each term in the document. Absolutely
Sir,
correct.
place
So,
of
yes. So basically, together with the, so basically, if we consider this as a document, together, I mean, earlier we were just storing how many times a term is occurring, right? Now, where they are actually occurring, those were not actually stored. So now, to allow this kind of a proximity-based operation, we should incorporate the information that is where this term is occurring, starting from say one position 1, 2, 3, 4, and so on. We should be storing the position of the occurrence of the terms as well, together with the term frequency. You are absolutely correct. Thanks a lot. So that is called basically a positional index. So let's say we have the terms in the collection, say information, library, and science. Let's say information is having a document frequency 3. That is, the term information is present in 3 different documents. And this will be basically the doc IDs. And the second is basically the term frequency. That is how many times the term is occurring in that document. And the next will be basically the position in which it is occurring. So information is present in the document having doc ID 2 only once, and the position in which it is occurring is 2. Considering that the document or the terms are being numbered from say 0th location, 1th location, 2th location, 3rd, and so on. Considering this, we will be storing the position as well. For example, for this term library, its document frequency is 4. That means library is present in 4 different documents. That's why there are 4 posting. The length of the posting lists is 4, right? The document ID is 2, 22, 45, and 34, basically 3421. In the document ID 2, it is basically occurring 2 times, and the position is 3 and 44. For the second document in 22, it is occurring again 2 times, and the location is or the position is 32 and 66. For the third document, the term frequency is 3. It is occurring in the position 3, 46, and 101, and so on. Now, how this information will be useful for performing the proximity search? It will be basically, given a document, given a query, not a document, sorry, what we will be doing is, as we are storing this as a third value, as we are storing the location, so let's say if we want to perform the search like information, ordered window to science, then we can see information is present in document number 2. In document number 2, libraries, sorry, science is also present. And 2 and okay. So all these two terms, information and science, is present in basically 2, 22 and 45 document, having document ID these three, right? Now, if we consider a simple term overlap, only term overlap based matching, all the three documents will be matched. But now, if we consider this operator, ordered window 2, that is, in between there can be only one term at most. Here, in the second document, the term information is present in the second location. The science is located in the fourth position. So there is one position taken by some other document. So this is actually a match. So 2 will be matched. Now let's consider 22. For 22, information is present in the location or the position 31. Science is present in the location 33 and some other. Again, here there is only one position in between. So this is also a match. Now let's look at the document 45. Information is present in the position 2 and science is present in the location 5 and 34. Now in between there are more than one terms, basically 3, 4, actually 2 terms. So that's why it will not be matched. This is the way we can actually perform this kind of a search, this kind of a proximity based search using a positional index. Now the other type of retrieval is basically a field based retrieval. Let's consider a research paper. So we know a research paper consists of many fields such as the title, the author names together with their affiliations, an abstract, an introduction, and so on. And some related work, some different sections, right? Together with that, there is another information stored is like what is the venue in which this is published. So this kind, I mean, if we want to perform a search, such as we want the term, say, word, or let's say, if we want the term, say model, should be occurring in the title, not in the word, or I mean, should be in the title, then there should be some provision of having a separate inverted index for each of the fields. Right. So let's say we want to search. So the author of this paper is Victor Lavrenko and Bruce Croft, W. Bruce Croft. So if I want to search like the term Croft or the term Bruce to be occurring in the title, in the author's field, it should not be checked inside the abstract or in the introduction. But in general, if we search for the terms in the only in the abstract or only in the introduction, it will be giving us wrong result, because we want the search with these terms to be occurring in certain fields. For example, I want the occurrence of model to be in the title, or I want the occurrence of either Bruce or Croft in this author field. So an obvious solution is to have separate index for each of the field, such as the title, author, the body, rest of the body, maybe the abstract separately. Using this, we can actually perform this kind of a search. And for this kind of a query process, this kind of a field-based index, the query processing is also pretty easy. So process each field-specific subquery. For example, if the query is phototherapy, it will be checked in title based on our need. And if we do not specify any specific field here, it will be basically checking all the fields, basically phototherapy in title, and or phototherapy in abstract, or phototherapy in body, and so on and so forth. It will be basically checking all the fields. And if we specify, if we want to, for example, for this example, if we want to specify a specific field for a term to be occurring, then we should be applying an AND here. For example, we want the term, say, Bruce, to be occurring in title, and there will be an AND clause. Say I want the term model to be present in the extremely sorry, I should, Bruce should not be in the title, but rather it should be uh, in the author domain, or in the author field, and this should be in the title. We can actually run this kind of a retrieval using this kind of a query. Let me, together with them, in this context, let me tell you this. When we have written the code using Python, using PyLucine, here you have seen that I have specified the title name, title, right? Plot. This is the need here. So in order to specify a field-based retrieval, PyLucine, or in general Lucene, comes very handy, because as we are storing this individually, we are essentially creating different inverted indices for individual fields. When we will be searching, we will be doing the retrieval using PyLucine, it will be much more clear. All right. The third type of query operators is basically called wildcard operators. So, for example, I want a query like it should be considering light therapy, light therapeutic, and all the variants of therapy, say. So this kind of query can be actually specified with a star here. Light and therap star. Now this therap star can be actually Y. In that case, it will be therapy. It can be IES. In that case, it will be therapies. And it can also be eutic, in which case it is basically therapeutic. So this will all should be equally considered for the relevance. Now, an obvious question is, do we need to modify the existing index to allow this kind of a query? Anyone? Okay, it will be clear in some minute. So Basically, what we are storing is we are storing the individual terms in the inverted index that we have stated earlier. To allow this kind of a query, one very lame way of applying or a lame way of taking the steps is using stemming. Why I am saying this is a very lame step, I'll be coming to that. So in the stemming, what we have done is we have basically stemmed the suffix. So therapy will be essentially be converted into therapy, pi. Therapies will also be converted into therapy. Therapeutic is, I think, also be converted into therapy. But as we have, no, I think we haven't seen that negative examples yet. But for some other terms, so let's say x is a root term and xs is the stem of it. It might be the case that xs is another root word y. It can be the case that they are equal. So, but here we want them to be specific to this therapy, variant of therapy. But as I said, this is the very lame approach that we usually consider. For fast lookup, we usually will be considering this stemming. Wildcard queries, this kind of a query will not be that much be covered. But still, let's have a discussion regarding that, how to actually consider or how to make the corresponding inverted index to consider this kind of a query. So what we can do is build a dictionary that maps the prefixes to the full form. For example, we will be keeping this as the key, and this will be basically a value, which will basically containing a list of words having the same keyword as the prefix. Now, during the query processing, given a query, we'll be looking up each prefix list, basically each the key in this dictionary, each of the key, and expand the query based on all these forms. For example, if the query is light and therapy, it will look like something, I mean, after extending, it will look like light and all the variant of therapy. Now, one small question, what binary or boolean clause should be here? Will it be and or will it be or? Anyone? Anyone, what should be the value of x? Correct. It should be or. This x should be or. So light and therapy or therapies or therapeutic. If we extend this, if I specify light as say A, therapy as say B, therapies as say C and D. So if we extend the query, it will look like A and B or A and C or A and D and so on. Also, this can be done in case of suffixes as well. Like eutic, it can be hermeneutic, pharmaceutic, therapeutic. And in case of a query like light and stareutic, we can perform this kind of a query. And how to actually handle this within term wildcard, such as say fetch list of full terms for the prefix therapy, therap star, and fetch list of full terms of suffix say star c. In case of the query is therap star c, then take their intersection. So basically, we will be first considering this. First we'll be considering this, then we'll be considering this part, and then we'll be considering their intersection. So this is the way we can actually represent this query language using some Boolean clauses uh, to transform an information need into its corresponding query form. Thank you. Any question?